Hello and welcome to this solving session, current series. So we'll wait for some time, others to join, then we'll start with today's session. Okay. So I welcome you all to this fourth session of problem solving session series, and Tanmay Saha, scholar at of Technology Kanpur. Today we'll be doing some of the discussions of the questions and assignment questions from your week 3 content, and then we'll go ahead and solve some problems, see some examples from the topics you have already been taught in your week 4 content, okay, in regular course. So proceeding ahead, start with the assignment questions out of your content. So the first question was the distance of the sprue the mold is defined by. Now design, to all the parts and parameters such as sprue weight, distance, then heat concentration is yeah. So flow distance is one of the parameter which is considered while designing a sprue. Okay, and then uh, mold layout is one. So consider the layout of the mold and the cavity. So these are very important factors while designing a sprue. And then you have this heat concentration factor. So this is obviously very important because the heat concentration factor actually decides uh, what kind of defects are going to be included when what will be your solidification time, thermal gradients during your solidification process. So all the three options are true, and so the layout of the mold and the cavity mount, the distance for the molten metal to flow rate, and the heat concentration define the distance between the sprue and mold. Sprue and mold system design requires all of the three options to be considered. Option D is correct here. Then you have one problem which asks you to calculate the volume of the mold and the height of the mold for a given set of condition. So we have in our earlier class seen problems related to calculation of uh, time, solidification time, and pouring time calculations. So it is a kind of similar problem where height of the downspout is given to 0.1 meter. Cross-sectional area was given as 0.85, 10 raised to the power minus 3 meters square. So the time to fill the mold cavity was given here. Mold filling time is provided as 1/22. Due to gravity is provided. The radius of the mold at the bottom is also provided, and at the top is also provided. So you have to find out the volume of the mold. Across uh, just a molded problem of the one we saw in our last class regarding calculation of the mold filling time. So say that if you look at the solution, the volume of mold is what? The mold filling time equation, right? So T is given by the mold volume, the ratio of mold volume, the choke area, AG, the gate area in this case, and then the velocity of flow, EG, okay? So which is given as square root of twice of GH. So HT is the total height in this case of the downspout. So the volume here is given as time of filling, which is given as 120 seconds multiplied by AG, which is actually the choke area, which is given as, sorry, it is 0.85 into 10 raised to the power minus 3. And then you have to plug in the equation for finding the velocity of flow. It is twice square root of twice gh, which is here 2 to 9.81 into meters. So it comes to be around 0.143 meter cube. Also, for a tapered cylinder, we know how to find out the volume. So the volume of here can be found out as pi here. So the area of the top and the bottom circular periphery, it is the top circle area, the bottom circle area, pi smaller square, and then the lateral surface area of the cylinder, which is 2 pi r h, right? You know, pi r h. So this one third of that gives you the total volume, and hence just plug in all the values to find out the height as 0.424 meters, right? I hope you were will able to solve this problem. So having said that, if we proceed, so the question says the degree of supercooling, right? So what is the supercooling degree related to? If you know what supercooling is, uh, it actually depends upon it is actually related to the crystal growth. So the necessity of supercooling is to start forming crystals, right? Is to start forming nucleation of crystals. Right? So when a surface is present that can act as an initial nucleation site for crystal growth, it significantly reduces the amount of supercooling needed for crystallization to occur. So already have an automatic formation of the first nucleation site, right? So you don't actually need to increase the supercooling degree here. So what happens is the degree of supercooling actually is actually reduced by the presence of a surface that serves as a initial nuclei for crystal growth. And then said that then the next question was when there is a sudden change in the flow direction, what effect is you are very much aware of this respiration thing now that happens due to that increasing of flow velocity around the sprue when the molten metal at high speed and gravity. So there is a mismatch or anomaly in the area as per the continuity equation is concerned. So a break of continuity actually leads to aspiration effect. There is a sudden change in flow direction. The area, sectional area of flow also changes. Aspiration effect comes to the picture. Okay. Proceeding to the next question. So which of the following is not a type of gating? So you all know about top gating and parting line gating as of now. So parting line gating is something a trade-off between the top and bottom, which takes care of the advantages of both top and bottom. The vertical gating is nothing like metal is poured in the top of the cavity. Okay, so there is nothing called inclined gating. So this is the wrong option here. The next question asked that suppose you have this kind of a screw design problem. So the dash in a mold is balanced by this. So if you see the pressure, yet we can only balance the pressure within a mold so that the continuity equation is maintained. And for that, a straight screw generally leads to a mismatch in the pressure gradient and aspiration effect comes up. So a tapered screw is generally used. Okay. Post blank filled with pressure. And second is followed as a tapered screw design. Then there is a question about permanent mold casting. A permanent mold casting uh, is a process that actually uses a mold to shape molten metal into a desired form, right? The molds for a permanent mold casting are made from steel, cast iron, and are able to endure repetitive use to produce dimensionally accurate thousands of parts and components. So in permanent mold casting, what happens is the molten metal is fed into the cavity in the metallic mold by gravity. So this is the correct option, option C. Then you have in a casted alloy, which of the following factors is independent to direction of crystal growth? So you have four options. So crystal growth, we had discussed in the first class that how uh, solidification is affected in case of a pure metal and an alloy. So in alloys, you see a range of temperature. You see a range of temperature above which solidification takes place, from freezing to room temperature, right? So there we discussed about formation of dendrites and different kind of grain structure, which actually leads to uh, variation in density, the finally built product. So yeah, alloy composition is something related to crystal growth. And then you have thermal gradient. Of course, thermal gradient is basic science uh, behind formation of dendrites. Okay. So thermal gradient is one of the important factors. Is the most important factor actually affecting crystal growth. The material aesthetics is not has nothing to do with crystal growth. So this is the wrong option here. I mean, as per the question is concerned, this is the correct answer. Okay. Then have which of the following is not true? So you have risers. If you know the use of risers, which is actually there to make sure the mold is always completely full. Then you have screw through which the molten metal flows, okay, and it connects the pouring basin and the runner or gates. Okay, so that's also true. And then you have a pouring basin to direct the flow of metal from ladle to gate. Okay, so this is reversely true. Uh, Molten metal actually flows from gate to the ladle. So this option is uh, wrong, and this is the correct answer is C here. So now it says top gating is used for. So we all know that top gating actually gives rise to a favorable thermal gradient, right? So top gatings in which hot molten metal enters the top of the casting, directional solidification. Okay, by this and because of favorable thermal, and that happens from the bottom of the top casting. So bottom gating systems have the opposite characteristics. The metal enters at the bottom of the casting, usually fills up the mold with minimal disturbances. Okay? But in this case, the thermal gradients get disturbed, and hence uh, directional casting is required for top gating, and while bottom gating is used for tall castings. Okay, so that uh, erosions, the wall erosions of the wall doesn't affect the quality of the part produced, right? Then we have this much actually summarizes your assignment questions from week 3. Hope you don't have any doubt. If you don't, then we proceed with discussing some of the concepts and problems out of your week 4 content. Okay? Okay, I hope you don't have any doubt with the assignment questions of week three, and we'll proceed with the content of week four. This is one question that I have designed, like what Keynes relationship is based on. This is the concept called Keynes relationship. So this is actually used to design risers. Okay, so riser design can be done depending upon the possible uh, factor, so that there are different ways to design risers, okay, such as Shodinob's principle, modulus method, Keynes relationships. So here, uh, as of now, let us go through this question, and then we'll go to the detail. We'll also discuss one numerical problem, the Keynes relationship for riser design. Was the end of today's class. Okay. The cooling rate is linearly proportional to the ratio of surface area to volume. So you can see from the graph only. So on the y-axis, you have the volume of risers to volume of casting ratio. And then towards the abscissa, you have the freezing ratio. So what is freezing ratio? It is actually the ratio of A by P, A being the area and P by the volume of uh, casting to that of the riser. Okay. So that will go through in detail in the upcoming slides. So as also you know that cooling rate is linearly proportional to the ratio of surface area to volume. So this Keynes relationship is used to actually design risers. So if the ratio falls uh, somewhere beyond this separating line, so then we have a sound casting, and then if it falls below that, we know we will have shrinkages. So accordingly, we have to take care of allowances for uh, uh, tackling shrinkages during the solidification process. Okay. Now, proceeding ahead, what should be the most appropriate design consideration for choosing dimensions of a specifically shaped riser? So we just discussed in the earlier slide that it is actually chosen to give a minimum area is to volume ratio, A by B ratio. Okay. And then which of the following region in casting shows the linear decrease in temperature. So there are different parts, the mold, the metal, which can be in the liquid, and then when solidified, it can be the solidified metal, and then you have the interface area between the mold and the molten metal. Okay. So so the linear decrease in temperature happens in the mold metal interface area, right? Then I have a problem for you. So there are two iron castings to be made. One is slab shaped and the other is spherical with a superheat temperature of 1560 degrees centigrade. And then it is a sand mold at initial temperature of 28 degrees centigrade. Now you have to determine the solidification time for a slab thickness of 20 centimeters, the first part of the question. And then you have second part in which you have a sphere of dia 20 centimeter. Now the twist here to note is there is superheat temperature of 1560 degrees centigrade, right? So the pouring temperature and the freezing temperature is different here. And I have given you some data. For iron, you have a density of 7850 kg per meter cube, a freezing temperature of 1540 degrees centigrade. You have the latent heat of 272 kilojoule per kg, and you have the specific heat for the molten metal as 0.46 kg per kilojoule per kg Kelvin. Similarly for mold, you have the density as 1600 kg per meter cube. You have the K thermal conductivity value of 0.8655 watt per meter Kelvin, and you have the uh, heat capacity of 1.17 kilojoule per kg Kelvin. So let's try it out, and then I'll show you the solution. Let's take care of the fact that one superheating process is just considered in this problem. try it out and then we'll discuss through the solution. So I hope you are actually trying to solve this problem. Finding solving this type of problems will help in actually clearing your fundamentals of casting process, how the thermal gradients govern the casting process, solidification process. So let's try, then we'll discuss. So it is said that two iron castings are to be made. Okay. So one is a slab of thickness 20 centimeter and one is a sphere of diameter 20 centimeter. Now I said that here one additional condition is there, that there is superheat temperature of 1560 degrees centigrade. So let's proceed with solving the problem. So if L, B, and H are considered to the dimensions of the slab casting, where our first half of the problem. So the volume of casting is given by V equal to LBH, right? And what is the surface area? It is twice of LB plus BH plus LH, you know that. And then here in this case, because it is a slab, right? It is a slab of thickness 20 centimeter. The height is very small as compared to the length and breadth. So we can just ignore the smaller terms, BH and LH, and the simplified area then becomes twice of LB. Then you have this casting modulus, which is given by the ratio of volume to area. So V is LBH and area is twice of LB. So the casting modulus then becomes half of H. Okay, so that is if H is 20 centimeter, then your CM or casting modulus becomes H by 2, that is zero point 0.1 meter. Okay. Now it is said that there is superheating. So the latent heat actually changes here. We replace that as L dash. Okay. Now, so the pouring temperature is not equal to the freezing temperature. So the L dash is then given by L, which is the ideal latent heat, and then you have plus Cm, the specific heat of molten metal, to pouring temperature minus freezing temperature. So you just plug in the values. So the latent heat is given as 272 kilojoule per kg in case of iron, that is the molten metal. And then you have Cm, which is again given as 0.46 kilojoule per kg Kelvin. And then you have pouring temperature, which is now the superheating temperature, which is 1560. And have the freezing temperature, which is 1540. Okay. So the newly modified latent heat L dash then becomes 281.2 kilojoule per kg. Okay. Then we find out the constants, dimensionless constants lambda and beta. I hope you are already exposed to this kind of problems and the derivations of this kind of parameters in your regular classes. So I'm not going to the details. We're just here to solve the problems. Okay. So lambda and beta, the dimensionless constants. So lambda is given as the ratio of the difference of freezing to initial temperature theta naught, and to the ratio of actually density of the molten metal, and the revised latent heat considering the superheat. Okay. And then it is multiplied by rho c, right? So then you have that lambda is 1.28. When you just plug in the values, 1540 as the freezing temperature, you have the initial temperature is 28, then you have 1600 as the density of the mold. Okay. And then you have C, the specific heat of the mold is 1.17 to 10 raised to the power 3. Then you have the density of molten metal, that is iron, here is 7850, and you have L dash as 281.10 is power 3. So calculate it out, find lambda is 1.28, and then you have for an infinite plane, beta is given as that is for a slab. Okay, slab, here you can consider this as an infinite plane. So it is given as lambda twice lambda by root pi. Okay, just plug in the value of lambda we found out from here. So you have the dimensionless constant beta is 1.44. Okay. Now we found out the two dimensionless constants lambda and beta, and then we proceed finding out the thermal diffusivity. Alpha is the ratio of conductivity to rho c. Okay. Then you have it as 0.8655 is the conductivity given for that mold material. Then just to plug in the density as well as capacity, the heat capacity value, you find that the diffusivity is coming out 0.46 into 10 raised to the power minus 6 meter square per second. So now alpha TS, then you are aware of these formulations. Alpha TS, where TS is a solidification time, is given by the ratio of casting modulus V by A square to the dimensionless constant beta square. Okay. So we have found out V by A to be uh, zero point 0.1 meter here, and then we have found out beta to be 1.44. Then using these plugging in these values, you can finally find out solidification time as 2.91 hours. Okay, and then we proceed with the next part of the problem where we have a sphere mold, sphere casting to be prepared. So here the dimensionless constant beta varies as lambda multiplied by 2 by root pi plus 1 by thrice of beta. Okay, so simply solve this solve this equation. So you have a, uh, 2 degree equation here. Okay. So polynomial of 2 degree equation. So you have beta is 1.69 or minus 0.25. When you solve this equation, you'll find these two values of beta. Now minus 0.25 is not acceptable as beta should always ideally be positive. So we pick up the 1.69 value and then simply go ahead and plug in the same equation alpha multiplied by solidification time equal to v by a square to beta square. So b by a for sphere we find out, as you know, the volume of the sphere is given by 4 by 3 pi r cube, and for a sphere the area is given as 4 pi r square. So the ratio then becomes r by 3, and r is given as so the dia was 20 centimeters, so r becomes 10, and this is the value of v by f for the sphere. Plug in these values and find out ts as 0.23 hours. Okay, so there is one interesting thing to notice here that when we consider the sphere, we have seen the solidification time has significantly reduced from almost 3 hours in the earlier case to zero point 0.2 hours in this case. Okay, why so? Uh, the answer lies in the geometry. So sphere is having the largest surface area, so solidification time automatically comes down, because this is a spherical geometry of cast. Just take a note of that. Then we move to the next problem, where we have to determine solidification time of a slab-shaped casting, 10 centimeter thickness, when casting is done in a water-cooled copper mold and casting is made in a very thick copper mold. So again, the important point to note here is for the first case where you have a water-cooled copper mold, it is a very thin, it's a thin wall of the mold. You don't have to consider the resistance from the mold. So this is a constant mold temperature, constant surface temperature mold casting. And then you have the second case where you have very thick copper mold. So you have to consider the resistance from the mold as well. So here you have both the mold metal resistance, and here you have only the molten metal resistance. So this is the variation in the two situations, and then I have given you these parameters which you may need to solve the problem. So for iron, the density is again 7850, freezing temperature is 1540 degrees centigrade, latent heat is 272 kilojoule per kg, the specific heat is 0.67 kilojoule per kg Kelvin, conductivity is 83 watt per meter Kelvin. Okay. So for the mole, the density is 8960 kg per meter cube. Conductivity is 398 watt per meter Kelvin, and then the specific heat is again 76 kilojoule per kg Kelvin. I have also provided this error function table, which you will need actually to solve this kind of problems, die casting problems. Just try out this problem again and then discuss the solution in great detail. Okay. So please give it a try and then we'll discuss the solution. Okay. So moving ahead, we had two parts of the problem again. In one, we have only the metal resistance. So the mold resistance can be ignored because it is a very thin water-cooled copper mold. So it is almost a surface, constant mold surface casting. And then you have a mold surface temperature casting. And then you have a casting which is a very thick copper mold. So again, here you have to consider the resistance from both the mold and the metal, but in any case, you can actually ignore the interface temperature, interface resistance. Okay. Now you have theta s is 28 degrees centigrade. Okay, and then you have it is from the earlier problem only, and you have the height as 0.1 meter. Then just plug in these values to the error function equation equated to this particular formulation. So you have xi e to the power xi square, error function of xi equals to the freezing temperature 1540 minus of the initial temperature 28 degrees centigrade multiplied as C, the specific heat capacity is given as 0.67 for iron. And then you have the L, that is 272 joule per kg, that is root pi. Okay? That is coming out to 0.1. Now, how do you find out the xi from this kind of equations? Is just you equate the right hand side and find out the xi values and the corresponding error function of xi values, which actually gives you this 2.1 value. Okay? So xi, uh, so there is a way to find it using this table only you do. So you have the right hand side to be 2.1. So just try out different combinations of xi and error function of xi and just see which xi value and the corresponding ERF xi value gives you this 2.1 RHS. Okay. Now in the problems or in the examinations, probably you don't need to start trying out all these combinations. You'll be given a range. Suppose for you'll be told that the xi varies from zero point 0.2 to zero point 0.3, zero point 0.2 to zero point 0.4. You have to try out these few combinations to see which xi value fits into this equation. Okay. So from that you find out psi to a 0.98, and then accordingly you find alpha as k by rho c. The values are again given for k as 83 for iron, and then for again rho c are given as 7850, and c is given as 0.67 into 10 raised to the power 3. So plug in the values to find the diffusibility value, which is coming out to 15.8, 10 raised to the power minus 6 meters square per second. Okay. I hope you got how to calculate this psi value, these equations, right? So then we'll proceed with calculating the solidification time Ts, which is given as again the total length of solidification, which is zero point 0.1 here. Then you have 16 xi square alpha s. So alpha we found out to be 15.8 into 10 raised to the power minus 6, and then again xi we found out to 0.98. So the solidification time in this case comes out to 0.0115 hours. Okay. Now this pretty much is the answer for the part one, where you are not considering the mold resistance, and then there is part two where the mold resistance needs to be considered. So here the error function equation will find two different forms, one for the mold, one for the metal, and these are all the temperatures which you are accustomed about. Okay. This is the initial temperature, and this is the surface temperature. Okay, then you have this theta's value from the earlier as 28 degrees centigrade, and then you just plug in all those values. The freezing temperature is again given, right, 1540, and theta naught is given as 28. So just plug in those values to find out this phi. This is the new term when it comes. So when you consider the mold resistance. So phi is determined as K rho C for mold to K rho C for casting. You just plug in the values for all those variables, and you find out phi is 0.57. Now, similarly, you just the way we found out xi in the earlier problem, we'll find out xi similarly in this case also. So xi to the power xi square, the one additional term which comes out is phi. So this we found out, which is related to the mold resistance. And then xi here comes out to a 0.15 once we go through this error function table. So then you find out the solidification time is again h square by 16 xi squared alpha. Just plug in the values is zero point 0.1 for total length of flow for the molten metal. And then you have 16 into the new xi is 0.815. And you have the diffusivity alpha is 15.8. It can still combine as 6. So the time now becomes 0.0165 hours, right? Is the problem again clear to you? Okay. Just try to have a look and ask me if you are facing problem in any ways in solving this kind of problems. And we'll move to our next part. Okay. So if you have got that, let us proceed with one final part of today's session that is related to cylindrical, that is related to riser designs. Okay, there are started when we started with today's session, we had seen the one MCQ problem related to Keynes relation. Okay, now this is one way of designing risers. Then we have uh, Sholnov's principle. We have modulus method of finding out or designing risers. Okay. Now this is a question which deals with a cylindrical riser for a sand casting mold. Here, the casting is a steel rectangular plate which have dimensions of 7.5, 12.5 cross 2 centimeters. It is say that previous observations have indicated that the solidification time for this casting is 1.6 minutes. and then you have to find out the dimension of the riser so that its solidification time now is 2 minutes. Having said that, the diameter to height ratio is 1 for the cylindrical riser. So this is an optimal case for side risers where the diameter and heights are kept equal. Okay, so then you just go on and calculate the dimensions of the riser so that its solidification time is 2 minutes. So here you can see the V by A ratio is required. So Chernov's principle is actually related to the ratio of V by A for casting and V by A for riser. Okay. Now for the casting, it is said that the dimensions are 7.5 cm cross 12.5 cm cross 2 cm. So the V by A ratio, then the area is again found out as twice of LB plus BH plus LH. So the V by A ratio is 187.5 by 267.5 equal to 17, right? And then this is the formulation from undergraduate level. You all must have seen. So this is solidification time. Then this is uh, casting modulus, and this is the constant. Okay, and then you have that TS, which is given as 1.6 for the earlier observed case. And just plug in the value of 1.6, and for the casting modulus is you plug in the value zero point 0.7. Then you find out gamma coming out as 3.26 minutes per centimeter square. So the you got it right. Now just have a look. Then we'll proceed with the next part of the problem. So this is how you find out the mold constant, and then sitting ahead, just you are given that for the riser, the D is to H ratio is 1 here. So the D is to H ratio 1 means the height and diameter are equal, and this is the optimal case as we discussed. And then TS, now the new time for solidification is actually 2 minutes, right? Now the volume you can find out pi square h by 4. You can say pi r square h, where since h and d are equal, okay, you can replace h with d. It becomes pi d cubed by 4. Again, the area is given by pi 2 pi rh or pi dh plus the surface area of the top and bottom surface of the cylinder, which becomes twice of area of 1, that is twice of pi d square by 4. Okay, so again you replace h as d, you find a as pi d square plus twice of pi d square by 4. somewhat gives you 1.5 by d square. Now, when you calculate the v by a in this case, you find out the result comes up to be d by 6. Okay, so this is for the riser, cylindrical riser. Earlier we had found v by a for the cast, okay, which is a simple steel rectangular plate. Now, by Sharnoff's rule, you can equate the new solidification time t, that is 2 minutes, equal to the mole constant 3.26 multiplied by the v by a ratio, that is d by 6 square. Right now, equating that, you find d is 4.7 centimeter. Similarly, h equal to d is also 4.7 centimeter. So these are the results which you are getting as per Sharnoff's rule, right? Now you just plug in the values, equation for volume of the cylindrical riser. You find out it to weigh 1.5 centimeter cube. What was the volume of the uh, cast? It was 187.5. Now, which somewhat means that the riser volume is only 44% of the volume of the cast plate, although its solidification time is 25% longer. So this much long time is not required, and so this is not an optimal design. It's not an optimal dimension which you have got. So in this case, you need to go ahead and check with the other principles also to see which one is giving you the optimal design. Now, just go through this problem once and ask me if you have any doubts, and then we'll proceed see two other methods of riser designs. Okay. Now moving ahead to the final part. Another method of riser design is called cane. So it means rather on the ratio is related to the area casting, surface area volume of casting, the volume ratio of riser. Have y value, volume ratio. The A, B, and C variables here are constants which are experimentally determined for a particular case. Fields A are 0.1 for one cases where material same for the cavity as well as casting as well. Now, so it is calculated to be one in that case. Otherwise, it is again experiment in sequence. You see that of ratio and a value, sorry, the ratio on the x ratio of the volume of riser to volume casting ordinate, the kind of, so it clearly separates one for casting and one where you can shrinkage. You're designing a riser, so riser dimensions, shrinkages and beyond this curve you all casting. So if value lies value comes shrinkage as okay riser to be covered by the riser volume. This is a pro and steels 25 casting for horizontal volume of the casting is casting twice LB twice of L run 5 and you have the volume of the riser and volume of casting, then you surface area riser is a cylinder equal d cube surface area is for lateral surface plus surface area top and the bottom, and you have top and bottom I described. Then you have this total surface area is 1.5 pi square ratio in the earlier slide. Surface area A by B fasting. Let's plug in the values here to a point. Then D is to be the value. Then you have which is again the dimension you need to find out. Then you have pi, actually the ratio of riser volume. Riser volume is 0.25 pi d. Then casting again 3-1 ratio y then substitute the formula right. It is 03 discussed one steals value of constants a, b, and c. 0.0. See that in this particular steel provided to you. You have one constant flow equation and d values to be which is again equal by trial error. This is how you solve again you have concepts you need to